Here's the type of voltaic cell that you might see in a textbook. The thing is, it doesn't do very much. Some numbers on a screen. Some numbers on a screen. Maybe stack a few together to make a battery and you'll light an LED. But what if you could get something with a little bit more sensory oomph? Now, how does that work? The problem with a lot of voltaic cells is their very high internal resistance. They struggle to power very much under load because the current is so low. And there are a few ways that we can remedy that. Job one is to increase the surface area of the metal to more than you would typically use for a classroom electrode. You could be fancy about it and trim a piece of copper sheet into a paddle shape so that the face sits on the bottom with the handle folded so that it curls over the rim of the beaker to secure everything in place. Or you might, like me, be in a small school without massive sheets of copper lying around, and that's where my trusted, uncoated modelling wire comes in handy. I also use this for a few other copper demonstrations, and it's easily obtained online from hobby shops. I've wrapped it around a 100 centimeter cubed beaker so that it will sit neatly inside a 250 centimeter cubed beaker. You can also find zinc wire for hobbyists, but given that the zinc only needs to be dipped at the surface of the liquid, you're more likely to have an appropriate piece in the stock cupboard. Again, a paddle shape will maximize the surface area, but I want to show you that the setup doesn't have to be neat to work. Something about this size will actually go. Add some water, tap water will do. Connect up the copper to a piezoelectric buzzer, some zinc on the other end. Dip in the metal and it's electricity. But probably not enough to get something like this little motor operating. For that, we need to understand what's happening when we dip in the zinc and make a few modifications. I use models like this to explain voltaic cells and redox chemistry. It's a simplified metallic bonding model with metal ions surrounded by free electrons. In the diagrams I'll use today, the size of the metal ions reflects not their actual radius, but indicates relatively how strongly that species can attract electrons towards itself. The smaller the representation of the species, the more tightly it will attract electrons. So in this case, I'm showing that ions of copper attract electrons more tightly than ions of zinc. If we add them to water then, in my representation, I show that water molecules are worse than the metal ions at attracting or accepting electrons. The electrons will stay on the metal. Metal ions can dissolve in water though, as evidenced by the lime scale you might find yourself having to clean from your kettle from time to time. Let's see what happens if we dissolve an ion from the surface of the metal into the water. If we use the idea that the copper ions will attract electrons more tightly and flip it on its head, we might suspect that fewer of them will escape the metallic lattice into the solution. Something like this. But as soon as the metal ions dissolve, a negative charge is left behind on the metal because there are now more delocalized electrons than positive metal ions. The metal ion in solution is going to be attracted back to the surface again, and the dissolving isn't going to continue because for every ion dissolving, the force pulling them back will increase. Unless we give those excess electrons somewhere to go. There are more excess electrons on the zinc than there are on the copper, so when we connect the zinc and the copper together with a wire, they can flow towards the copper. Great! It appears as if we can measure the voltage at this point and find something that looks close to the difference between the standard electrode potential of zinc and that of copper. If we allow these electrons to move, and of course in theory they can't through a voltmeter, then more zinc ions can dissolve and we can start to form a zinc solution around the zinc. But at the other end, we will almost immediately run out of copper ions in solution. Strictly speaking, oxygen in the water is also playing a role here, but you can check out the supporting article for more on that, link below as always, or the previous exhibition chemistry nailing corrosion demonstrations. Let's keep it simple for today and focus only on the copper. If we want the process to continue, we'll need to add some copper ions in there to replace those that we lose. And this is where some of my tips come into play in order to get a cell that will run a motor. Now, these types of cells used to run the telegraphic network in the UK, the US, and so they needed to be easily maintained, and the instructions were pretty much get copper, get zinc, add distilled water, chuck in some crystals of copper sulfate, and then don't touch it. Now we've got the crystals out, it's eye protection time. Why not move the beaker once it gets going? Well, let's think about what's happening. I put in my crystals, drop to the bottom. Now at the base of the beaker, a highly concentrated solution of copper sulfate will form. Being significantly denser than the dilute solution forming overhead, it will hang around near the copper at the base. This is a good thing because if the copper ions were to stray up to the metallic zinc at the top, then all of the energy that we wanted to operate the motor will be lost as heat in a displacement reaction. The other thing holding the copper ions at the base is that as long as current is flowing, we'll have zinc ions dissolving up at the surface, and they will be migrating downwards towards the copper. The positive ions are moving towards the base of the beaker, and this supports that difference in density in keeping those positive copper ions towards the base. Eventually, enough zinc ions will have dissolved up top to reduce the resistance in our electrolyte to operate the motor. But we don't want to have to wait for that. So I give my cell a bit of a kickstart by beginning in the solution. Instead of water, I use 0.1 molar zinc sulfate solution. The concentration really is not important because, like I say, water would have done the job. It's just that if we go too much higher in the concentration, we'll begin to lose that difference in density, keeping the copper at the base, and also introduce a couple of extra hazards to the zinc sulfate solution. I also add a couple of drops of 1.4 molar sulfuric acid, and this really is an optional addition because if done in front of students, it might confuse them. My reasoning here is just to increase the conductivity of the solution, and we saw in Shocking Revelations Part 2 how much more conductive acids are than other ionic solutions because of the way that the protons move from molecule to molecule instead of the whole ion having to migrate through solution. Now when we connect the motor with the more conductive electrolyte and the plentiful supply of copper ions at the base, the motor should stutter into life. And I just want to show you that you can have a massive impact just by lowering the zinc a little bit further. Making sure that you've got really high surface area is the trick to keeping this going. Once it starts, it will continue until either the crystals are exhausted or all of the zinc has dissolved. Longer than a lesson, I would say. You can recycle most of the materials here if you've made some of the metal paddles I suggested rather than this sort of rough and ready approach that I've gone for, and you decide not to use them again. They can be trimmed into metal strips for class use. The zinc solution from above can be syringed out and reused. This one here is actually one that I was actually using before. The layer that's sort of in between, if you've got any copper-zinc mixture, that can separately be collected into a mixed copper-zinc waste solution bottle, and that itself can be upcycled. CLEAPS members can see the disposal guidance from TL003 for how to do that, and the lower liquid can be left to crystallize. The crystals that are in here are actually ones that I've collected again from having done this demo before. If you've got that stuff at the base, you can just pick out the copper sulfate crystals and use them again. As soon as you first hear the chirp of the buzzer for this demo, you just want to play with this setup. It's as an initial voltaic cell to explore. I find it so much more intuitive than seeing numbers on a screen and having all of the extra faff of a salt bridge. So give it a try and let us know how you get on.